Hello again. Thanks for joining us. This is Space Nuts, the Astronomy Space Science podcast. And I'm your host, Andrew Dunkley. And coming up on today's episode, we will be looking at Venus. It looks like there's a new theory, perhaps a new study, that suggests that Venus was a once pristine, livable, beautiful planet until the volcanoes took over and turned it into a seething hot mess. We'll look into that. And strange cosmic filaments and threads have made the news. It's a fascinating story, and we'll be talking about that as well. Also, questions about antimatter, anti-protons, space junk, relativity, and riding an exercise bike. Don't ask me. I'm throwing that one to Fred. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
We've got an exercise bike in our place. It's a beautiful decorative item that sits there and does very little. And joining me, as always, is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. My exercise bike actually goes places. You get on it and it takes you somewhere if you pedal. It's fantastic.
I've heard of those.
Yeah.
Yeah. I my entire childhood, I spent on a push bike. I rode everywhere.
Yeah.
And I was even my own mechanic. I could do everything. You look at the young people these days. I could fix flat tires. I could change wheels. I could replace a cotter pin.
Ooh, that's serious stuff because they're on the pedals, aren't they? The cotters.
They are.
Yeah.
Yes.
Yeah.
I very handy with a bike.
Good.
Well, I even started a little business reconditioning push bikes.
When you were a youngster?
When I was a teenager. So I'd get an old bike and I'd fix everything up and then repaint it and sell it.
Well. And that's how the legend was born.
I didn't like it. I got fed up. You know what young people are like. That lasted 5 minutes.
Yeah. Well,
it was fun. I loved it. Now, Fred, we have got plenty to talk about. And let's first focus on Venus. Now, this is a planet that, in size at the very least, closely resembles Earth. But as we have discussed in the past, it used to be much more Earth-like and possibly livable. And at some stage in the history of our solar system, Earth, Mars, and Venus were probably all livable planets. Ours is the only one left. But now there's a suggestion that Venus might have been transformed by something that we have seen a lot of on Earth, particularly in recent times, volcanic activity, and it might have tipped them over the edge.
Yeah, that's it in a nutshell, Andrew. Absolutely.
Okay, next story.
So, just to explore the nut inside the nutshell, yes, you're right. The prevailing theory is that Venus might not always have been the hellish place that it is now, and that something triggered a runaway greenhouse effect. And of course, Earth could be on the brink of one of those as well. There are tipping points in the climate. I think we're certainly not near the tipping point for a total runaway greenhouse effect like you get with Venus, but these tipping points are real, and if you think Venus has got a runaway greenhouse effect, and we all do, then you will be looking for something that triggered that actually pushed a climate which we believe was quite benign, as you've said, in the early history of Venus, into the regime where it is now, where the surface temperature is roughly 460 degrees Celsius. And the pressures, if I remember rightly, it's 90 atmospheres. It's nearly 100 times the pressure of the surface on Earth. So very, very different, and lots of carbon dioxide in the atmosphere. So what has happened is that scientists who are based at NASA and elsewhere, in fact, one of them is at Goddard Space Flight Center. The Goddard Institute for Space Studies, which is in New York. That's a NASA institute. A gentleman by the name of Dr. Michael Way it refers to something called large igneous provinces.
Oh.
And large igneous provinces are apparently the result of volcanic activity that may have lasted between hundreds and thousands of centuries, not years, centuries, and delivered colossal amounts of magmatic material to the surface of the planet. Now, there's evidence that the Earth has gone through phases like this. And the suggestion is that some of them may have caused mass extinctions. The one that comes to mind, and I really don't know very much about this, you might know more than me, Andrew, is the Deccan.
You're right.
The Deccan Traps in India, which I think is a region of huge lava flows, which are thought to have occurred not at a dissimilar time in the past to the extinction of the dinosaurs because of the asteroid impact. And I think I've seen some suggestions that the instability in the Earth's crust that was caused by that impact 66 million years ago may be what upset the balance and caused this huge outpouring of lava, which resulted in the Deccan Traps. So we do know that sort of things happened on Earth. But the really interesting aspect of this research that we're talking about from Dr. Way and others is that on Venus, about 80% of the surface is covered by these lava fields, large areas of solidified volcanic rock. One of the comments that Dr. Way made was, well, we're not yet sure how often the events that created these fields occurred. We should be able to narrow it down by studying Earth's own history. So here's a way in which we can look at examples on Earth, and maybe the Deccan Traps are one of them, that you could perhaps use as models to study Venus's history. And they go on to say that in the last 500 million years, and that's about how long multicelled organisms have been alive on our planet, there have been about 5 of these major mass extinction events that got rid of about half of the animal life on the planet. And the studies that have been made, including this one, suggest that most of these events actually were caused or perhaps even made worse by the eruptions that produce these large igneous provinces, these fields of lava. So the comments that's made is that in the case of the Earth, the climatic disruptions that those extinction events and those volcanic periods of volcanic activity, the climate disruptions weren't enough to trigger a runaway greenhouse phenomenon. But clearly it was on Venus, because that's what we see today, the effect of a runaway greenhouse with this surface temperature in the 400s of degrees Celsius. And so this is part of ongoing research, I think, to find out why something like that didn't happen on Earth. It didn't trigger the runaway greenhouse, but it seems that it might have done on Venus. To my mind, if you've got a planet that's covered by 80% of its surface is covered by solidified lava fields, then that's a pretty good answer as to why you might have a runaway greenhouse effect when you compare it with a planet that's covered by 75% of its surface is covered by water. In other words, our planet. And so the researchers point to the upcoming missions that are heading to Venus. We have 2 NASA missions which are scheduled for the late 2020s, Da Vinci and Veritas. Those are both rather neat acronyms. Da Vinci is Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging. What else? And Veritas is Venus Emissivity Radio Science, INSAR, that's radar, I think, topography and spectroscopy.
So they spend millions on committees to come up with all these.
Well, if it's anything like the ones we came up with when I used to build scientific instruments for astronomy, you do it when you're in the bathroom and places like that. Oh, I know what's a good name,
Yeah.
In fact, I remember thinking of the first instrument I built was called FLAIR, the Fiber-Linked Array Imagery Formatter. And I remember the moment I thought of that was in the car driving home from the observatory. So there you go. These moments stick in your memory. That would have been, nearly 40 years ago. That's right.
Wow.
Anyway, the idea behind these missions, and we actually have talked about Da Vinci and Veritas before, but not very much. We've just mentioned that they're there. They are, I think they're probably heading to Venus together. But they've got very different views. I think one's a lander and one's an orbiter. I can't remember. Yeah, Veritas is an orbiter. And Da Vinci is deep atmosphere. So, yes, it goes right down to the bottom of the atmosphere.
I can imagine the orbiter will get there and send back a signal saying, yeah, it's still yellow.
Yeah, that's right. Like it was before. Anyway, we will await to see what happens in the late 2020s with these. Really interesting work. It would be great to understand why Venus triggered, or some activity on Venus did trigger a runaway greenhouse effect, just to rule it out as a possibility in our own planet.
Could the volcanic activity have anything to do with its proximity to the sun? Could that have been a factor?
Well, it must make a difference, yeah. So, you're absolutely right there. And the three planets, as they sit today, naively, you could say, well, Venus is much hotter than Earth. Earth is like the Earth. Mars is much colder than the Earth, and they're in order of their distance from the sun. But we think there's much more to it than just that, than just the distance. But it's clearly a factor.
It's the Goldilocks effect.
Yes, the Goldilocks effect.
Cold, too hot.
Here's Goldilocks herself.
Hello, Marnie.
Goldilocks has just arrived.
Bye.
Bye,
I'll
darling.
see you tonight.
So, heading off to fly to, where is it?
Adelaide and Brisbane.
Brisbane and Adelaide today.
Wow. Okay. Nice.
A very glamorous Virgin cabin.
I'm sure it is.
Goldilocks.
See you later.
Bye.
Bye.
Have a good flight, or have 4 good flights, actually.
Yeah, gosh. It looks glamorous, doesn't it, being an air hostess or steward or whatever, but it's hard, yakka.
It is hard, and Marnie's feeling it at the moment as well. She's taking all the time that she gets off between flights to recover from the flights.
I'm sure.
Yeah.
I'm sure.
Anyway, we'll see how it goes. So far, so good.
Yeah. All right. So the sun could be a factor in the volcanic activity that seems to have caused Venus to go over the edge and turn into a massive greenhouse.
It could.
Okay. Now, we just as a side observation, we've had people in the past quiz us about whether or not we could terraform Mars and then Venus. We got a question from Buddy in Oregon the other day asking if we could build something to shade Venus one day, and maybe that would settle it down. But I think it's probably reached a point where it's self-perpetuating, is it not?
Yeah, well, that's right. So, I mean, it's in an equilibrium now. So the runaway greenhouse effect has kind of settled down and reached its climatic conclusion of a temperature of 460 degrees Celsius and hot enough to melt lead and all of that stuff.
Yeah.
So the idea of a megastructure, which is what I think Buddy was talking about, is, it's fanciful engineering at the moment. We can't do anything like that. But even thinking about whether you could, the question is just what sort of thing it would be. Maybe a big metal plate at the L2 point, the Lagrange point between Venus and the Sun, where there would be a gravitational balance. The trouble is, what would happen then is the metal plate or the shield or whatever you built would get hot and just start radiating infrared heat back to the planet, maybe you'd make it shiny enough that it reflected the heat back to the sun. But if you're talking about mega engineering like that, who knows what effect something like that could have on the sun? My guess is that Venus is always going to be a world where humans are really not allowed to stand because they would just melt. And the opposite is true of Mars. Mars clearly has potential for human exploration, but I think most people would think, megastructures notwithstanding, I think most people think Venus doesn't have any potential for human exploration. But things like Da Vinci and Veritas will do the job for us, and they'll do a great job.
Yep. Okay. It looks like a very workable theory as to why Venus turned out the way it did. This is Space Nuts. Oh, by the way, you can look up that paper in the Planetary Science Journal. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, Fred, to our next story about cosmic filaments, cosmic threads, cosmic things, whatever you want to call them. I must confess my ignorance of this story because I really don't understand this stuff very much at all. But there is some new information to hand, so over to you.
Yeah. I mean, to be honest, it's well outside my field of expertise as well, because these filaments are strange thread-like features that are observed at radio wavelengths. And in fact, it's fairly easy to find, I think, a Meerkat image. Meerkat is the radio telescope array in South Africa, which is forming the nucleus of this mid-frequency square kilometre array. We've got a lot to do with it here in Australia because there are opposite number at the mid-frequency end of the spectrum compared with the low frequency, which Australia's doing. So these are frequencies, if I remember rightly, it's something like... anyway, it's up to 15 gigahertz I know that's the maximum that Meerkat looks at, and SKA mid. So these are quite high frequencies. So they're different from what we use when we're just looking for cold hydrogen in space. But it is what you're picking up with this is energized streams of gas. It sounds like Marnie taking off there. I don't know.
Yeah, I heard that.
She's been very quick to get to the airport. The filaments of gas that are magnetized, and that makes them emit radio waves. But they're weird-looking things, really weird. They almost look like something alive, Andrew. But of course, they're thousands of light years long. These filaments, they're thin, they're long and thin. They're thousands of light years long, and they're caused by magnetic activity. They're remarkable, and there are some extraordinary images from Meerkat, of the filaments in our own galaxy. Now, the reason why this story is in the headlines at the moment, at least in the Space Nuts headlines, is that for the first time, scientists have observed these magnetized filaments in other galaxies than our own. And so that's not been something that's happened. There's around 1,000 of them are known in our own galaxy. As I said, up to hundreds of light years long. But the reason probably why they haven't been observed yet in other galaxies is simply because they're too faint. They're small and faint relative to the size of a galaxy. And that makes them difficult to detect. But with this work, which I think most of this has come actually from Meerkat, Meerkat is a very sophisticated array of dishes in a very radio quiet region in the High Karoo of South Africa. And so Meerkat's opened a new window, particularly on the galactic center. I've seen some incredible images of the galactic center that have come from Meerkat. But they've also now trained this array on other galaxies. They've looked in clusters of galaxies, which is a good idea because looking in a cluster brings up more galaxies. And these range from 163 million to 652 million light years away. So it's 4 different galaxy clusters. And they've been detected. And sure enough, they look like the filaments. They look at first sight like the filaments in our own galaxy, but apparently there are differences. And one of them is that, unlike our own galaxy, which is fairly quiescent quiet galaxy. Its black hole in the middle isn't doing that much in terms of gobbling stuff up and releasing energy. Some of these galaxies are, though, they've got active black holes at their center, and that means they push out jets of material, become what are called radio galaxies. And those filaments seem to be associated with those jets of material. And actually, the filaments, it seems, are much bigger than the structures that we see in the Milky Way. And that might be one reason why they've been detected, because you're actually looking much, much further away than we are at our own galactic center. And so if you detect filaments, it's likely to be ones that are bigger. And in fact, they suggest they're between 100 and 1,000 times larger.
Yeah, I mean, I'm reading numbers like 200 kiloparsecs for the length of some of these
That's
things.
right.
That's just mind-bending.
It is
distance.
Yeah. So a kiloparsec is 1 kiloparsec is 3,230, I think, light years. It's a kiloparsec, 1,000 parsecs. A parsec's about 3.23, if I remember rightly, light years. So yeah, you're talking about things that are nearly 700. 1,000 light years, which is bigger than the size of our galaxy. So we are talking about things that are quite different in scale to the ones in the Milky Way, even though their appearance is quite similar. And the other thing is that some of these ones associated with the jets of material squirting out from black holes at the center of active galaxies, the filaments come out at right angles to the jets. It's very, very weird. The ones in the galactic center, of the center of our galaxy, seem to stick up and downwards from the disk of the galaxy itself. So they are, again, they're at right angles to something, but it's not a jet squirting out of the black hole at the center. It's the plane of the Milky Way itself, the disk of the Milky Way. So very, very odd stuff. And I'm not sure if people fully understand how these things are formed. The radio astronomers talk about winds. Galactic winds are things that come from supermassive black holes. We think of the solar wind, the wind of subatomic particles coming from the sun. Well, you get galactic winds as well, which shoot out into the space between the galaxies, which is otherwise pretty empty. So they're suggesting, that those winds actually, as they blow, they might push material together to sort of create these filaments, which is probably as good an idea as any. But I think they've got issues with that, because there's things that we don't understand, turbulence in the galactic winds, things of that sort. It looks as though the jury is really out on exactly how these filaments occur and why they come about. And so I think this is an area of research that will go on and get much more prominent. And I, for one, would like to understand it a bit more. And so I hope you and I will talk about it again down the track, Andrew, when perhaps there's new results coming.
From what you've said and from what I've read, these things, other than having a purpose, are more likely just an effect of something else. Would that be a fair assessment?
I think that's absolutely right. So, there might be an effect of these winds and the way the winds blow, if I can put it that way, galactic material together to create these things. It's very, very interesting. There's you and I are reading the Science Alert article on this, which is very well written by Michelle Starr. Lovely name for an astronomy journalist. And if I can just quote Michelle, when she's talking about these galactic winds, winds could be one such mechanism. And apparently simulations have suggested the possibility of turbulence in the galactic medium. That's the thin gas that's inside the galaxy, generated by gravitational disturbances. This turbulence can create eddies in the intergalactic medium around which weak magnetic fields get snagged, folded, and ultimately stretched out into filaments with strong magnetic fields. And that's what we see. But as she goes on to say, it's not a definitive answer yet. So, yeah.
It's probably just static electricity.
Well, that's when I looked at the picture, the meerkat picture of the center of our galaxy, that was actually the first thing that I thought of, because they look a lot like those, what they call the sprites that come out of the top of thunderstorms. These discharges, they're electromagnetic discharges from thunderstorm activity, which we've only really been aware of for the last 20 years as digital cameras have allowed us to photograph them. Sprites and other high energy phenomena, reddish coloured streaks of light that go vertically upwards from thunderclouds. And that's kind of what they look like.
It is, isn't it?
Yeah.
Very odd. Well, hopefully one day, hopefully soon, we'll learn a bit more about them and find an explanation. But their sheer size suggests there's something significant going on, more so in other galaxies than our own, by the look of it.
That's correct.
All right. You can find out more about that at the Science Alert website. You can also read about it through the Astronomical Journal letters, where the research has been published. You're listening to and watching Space Nuts with Andrew Dunkley and Fred Watson.
0G, and I feel fine.
Space Nuts.
Now, Fred, to our least favourite part of our favourite part of the show, where we hand it over to the audience, and we've got we've got 3 people asking about 5 questions.
Yeah, that's reasonably concise compared with some of the ones we get.
Yes. So first up, we are going to hear from Fenton.
Hello, Fred and Andrew. This is Fenton calling you from Minnesota in the U.S. You were talking about antimatter, as I heard, and that led to one question that I had. That is, now you've been talking about antimatter electrons. Great. What about antimatter protons? That is a negatively charged proton. Has anyone tried to detect or prove them? What happened? Is it realistic? I would love to hear your response on this and your thoughts. Thank you very much, and have a nice day. Bye now.
Bye, Fenton. Thank you. And the answer is yes. And now Chris has a question about...
It's lovely, Fenton, to have a straight question to which we can give a straight answer. Because normally we waffle, don't we? Really?
Speak for yourself.
I'll do my best. It's a great question, and Fenton's absolutely right. Whenever we've talked about antimatter, we've talked about positrons, which are positively charged electrons, the antiparticle equivalent of an electron. But yes, the antiproton was predicted by Paul Dirac in 1933 and first experimentally detected in 1955 at the University of California. Both of those discoveries, Dirac and the experimental confirmation, both of them netted Nobel Prizes for their proponents. So, so the antiproton, a very well known and well studied example of antimatter. So there are other antiparticles. I think it's fair to say, and I'm not a particle physicist, but I think this is true, that every particle that we know about has an antiparticle equivalent. So the composition of an antiproton is 2 up antiquarks and 1 down antiquark, which makes it a hadron with fermionic statistics. It interacts with the strong and weak nuclear forces, with the electromagnetic force, and with something called gravity. So, yeah, it's got everything going for it. It's exactly what you'd expect the oppositely charged equivalent of a proton to be, and it is an anti-proton. And it's lovely to be able to talk about it, because we don't often talk about anti-protons.
No, I don't. I can't recall us ever going down that road before. So.
Yeah, just a little postscript here. They were detected first in cosmic rays, first detected in 1979 by balloon-borne experiments. So, yes, they occur in nature as well as in particle colliders, which is where they were first identified.
Okay. There you are, Fenton. A definitive answer at last.
Yeah. To a great question. I'm very glad Fenton asked.
Terrific.
Yeah.
Thanks, Fenton, and always good to hear from you. And now we've got a couple of questions from Chris.
Hey, Fred and Andrew. Chris from Canberra here. I've got a couple of questions for you. Firstly, with all the space junk being dropped by SpaceX in our national parks, shouldn't we be finding these polluters and making them pay to do a cleanup? My second question is a matter of relativity. Recently, there was a question regarding time dilation in a spacecraft with 1g constant acceleration. I was wondering, is that 1g acceleration, is that from the perspective of an external viewer or one on the spaceship? Seems to me that it would be likely to be an external viewer, observer. And if this was the case, then the acceleration for the internal observer would be much higher than 1g. What do you think? Thanks. Keep up the great work. Really enjoy the show. Bye for now.
Thanks, Chris. Yeah, that's a good one. Well, I suppose we should tackle space junk first. And I know he's probably referring to a piece of junk that landed in Australia not so long ago. Did it land in a national park or on someone's farm? But either way, I think it was a piece of SpaceX, wasn't it?
Yeah, that's right. So, and it's not too far from where Chris is in Canberra, because this stuff.
That's why it's front of mind.
It's front of mind. It came down in the Southern Highlands of New South Wales, and it's several bits of debris which have come from the service module of SpaceX's Crew Dragon, the Crew Dragon capsule. It has its own service module, which is supposed to burn up on re-entry. The Crew Dragon capsule itself is not supposed to burn up on re-entry because it's got astronauts inside it. But the service module that provides all the power and heat and light and everything for the crew module that burns up or not, as the case may be. And several bits of one of these have landed in the Southern Highlands of New South Wales, not too far from Canberra. Some of it's in the Jindabyne area, I think, which is in the Snowy Mountains. And I was going to say, these have all been investigated in some detail by my colleague Brad Tucker, who is an astrophysicist at the Australian National University. So he's in Canberra, and I think he's visited several of these sites of debris impact just to go and check out what it is and have a look at it and smell it and all the rest of it. But Chris is right in that space law says that whatever country puts something up there, they own it and are responsible for it when it comes back down, as well as when it's in space. And it is a national thing, because it's the space agencies of the individual countries that actually ratify the launches. So, yes, there is an argument to say that somebody who drops space junk on and damages property, and if that was the case, property was damaged, then the organisation or nation that was launching that would have to make amends and make reparation. Now, I don't know whether this latest tranche of space junk from the Crew Dragon service module has damaged anything. My understanding is it's all landed in open paddocks.
Yes.
And it's more a curiosity than anything else. But if push came to shove, space law would say that, I'm pretty sure space law would say, I'm not a lawyer, I do know some space lawyers, but I'm not one, I think it would say that compensation would be due, and you'd have to make good.
Okay. Well, that makes sense, but I got a feeling nothing came of this. And
not. I think in this instance, because as I said, it's just if it hit a farmhouse and especially if there was if there was injury or worse, a fatality, and there never has been a fatality caused by space debris. But it's given the amount of stuff that's going up there now, particularly with reusable Falcon 9 launchers, there's a really good chance that there might be something much more serious happening. And in which case, all these space law legislations will be tested, and we might find cases where this actually holds good.
Yeah. Okay. I had read recently that a lot of the future satellites will be much smaller because advances in technology are enabling them to do that. So a lot of those are likely to burn up completely.
Yeah.
So that reduces the risk going forward, but
it does.
With the big boosters and things like that, that could be a different story.
Yeah. That's right. It's the biggest bits and pieces. I mean, SpaceX's Starlink satellites, they're not small. They're 3 meters by 1, and they weigh 1/4 of a ton. But that's still not too big to burn up completely. So they will burn up completely. In fact, some of them already have.
Yeah. All right. There you go, Chris. So yes, they are responsible, but good luck in court.
Yes. So part 2 of Chris's question.
Yes.
About the acceleration. So certainly the thing I envisaged when we were talking about accelerating a spacecraft at 1G, so you nicely get artificial gravity as well as a fairly rapid acceleration up to close to the speed of light. That 1G is the acceleration as experienced by or as observed by the occupant of the spacecraft, not by an external observer. Okay. Because the external observer, who's in a different rest frame, will see a relativistic effect. There is, special relativity not only tells you that a stationary observer sees something going at a different speed from the moving observer and sees time dilation and all the rest of it. The stationary observer also sees a different acceleration. And there is a well-established mathematical theory, which is a bit ugly looking when you look through it, and I'm scanning through the equations now, which covers relativistic acceleration. And if Chris wants to have a look at those, you can go to the Wikipedia page called Acceleration in brackets Special Relativity, and it will give you these awful accelerations. And as always, when you throw relativity in, there are factors of 1/c² in it, the speed of light squared. For example, the Lorentz factor, which is what changes the apparent relative velocities between a stationary and a moving observer, is 1/√1 v²/c², where v is the velocity of the moving object. So
I just got a headache.
Yeah, they all look like that. All these equations have got this 1/c² in it, with one exception, which is E equals mc², where it's a multiplier rather than a divider. So yeah, it's a very, very much the province of special relativity. And so yes, there are acceleration differences which come about because of those effects.
Okay. There you go, Chris. You asked the question. I'm just the messenger.
So am I. Don't shoot the messengers.
Okay, from Canberra to Donnybrook. Now, I don't know where Rusty's coming from on this one, but we'll see if we can figure it out.
Good morning, Fred and Andrew. It's Rusty. I had a really interesting experience this morning on my exercise bike. I was doing 20-second sprints, and I noticed that my clock started running slow towards the end of my sprints. So I thought, well, this proves the special relativity theory wrong, doesn't it? Stop laughing, please.
Oh, yeah.
Anyway, then I realised
how did you know we were
two things. One, I wasn't really doing near the speed of light. It just felt that way. And 2, the clock was actually bolted to the frame, so it was probably right after all. 2 questions. Did Einstein have a push bike when he worked in the patent office and a watch? Maybe that was his eureka moment. Anyway, it's a thought that counts, isn't it, Fred? Cheers, guys.
Thanks, Rusty. Never seen you at the Olympics, so I suspect that someone else was slowing down rather than reaching near the speed of light.
Is there an Olympic event in exercise bikes? I wasn't sure about that.
Even if there was, I'm not sure Rusty would get in.
Oh, ye of little faith. You never know. Rusty might have talents that we're just simply unaware of, as well as being a relativist.
Well, if he's as good as he sounds like he is, he's got legs like tree trunks.
Yes, that's right. So I think given that his exercise bike is bolted to the ground, I think you can rule out special relativistic effects because you've got to be moving with respect to something. And now, yes, it's bolted to the ground and the ground's moving with the rest of the planet. But that puts us all in the same reference frame. It doesn't mean that there are relativistic effects between an exercise bike rider and his bike. I think there's a paper in that, actually. I think there might even be a PhD in it.
Right.
The relativistic effects of an exercise cyclist. I suggest the reason why his clock was running slow was because it's faulty.
I was going to say it was caused by WLS.
Wait a minute. WLS. What? No, go on.
Weary leg syndrome.
Okay. There's the opposite of what you get in bed. Restless leg syndrome. Yes, that's right. Which my wife complains about all the time. So I think the to look for a relativistic reason why his clock's gone slow, I think you'd have to invoke gravitational time dilation rather than special relativity time dilation, which probably means it may be to do with if Rusty's been putting on weight or something like that on the exercise bike and the gravitational field has changed, that could cause this clock to slow down.
Oh, boy. I wasn't going to go there. I'm disappointed I didn't think of it first.
Did Einstein have a push bike? Yes, he did. There's a famous picture of him cycling around somewhere. It's nearly as famous as the one of him with his tongue out. But his eureka moment, and he had a watch as well, his eureka moment was a kind of thought experiment, a bit like that. Not him riding on his bike and looking at his watch. But the basis of general relativity, the gravitational theory, is the equivalence of acceleration and gravity, which we've already talked about with the idea of providing artificial gravity when you accelerate to nearly the speed of light. So he thought of this experiment when he was working in the patent office. He imagined himself going up to the top of the building and jumping off, and what he would experience as he fell to the ground. And it was when he realized that if he did that, he didn't do it, but if he had done that, then, the coins would have floated out of his pockets, his pipe would have floated out of his mouth, because they're not feeling any gravity. And it was then that he realized that he's being accelerated by the pull of the Earth's gravity. And that kind of negates the gravity of the Earth. And so that was why he saw the two as equivalent, gravity and acceleration. And it became something which I think he published in 1912, because he thought of this in 1907, described it as the happiest thought of his life, Andrew.
Wow.
Yeah, that gravity and acceleration are equivalent. And that became the special theory of relativity. I think he published in 1912, he said.
Good grief. Yeah. What an amazing mind.
Yeah,
though.
incredible. Just incredible.
Unlike Rusty.
Well, I do like Rusty's thinking.
He's got a great mind.
Yeah.
That's all right. He's Australian. He knows we're just taking the mickey.
He does. Well, he's taking the mickey out of us, so we might as well do it back to him.
Yeah, indeed. Thanks, Rusty. Interesting questions. We're done, Fred. A reminder that if you have questions for us, please send them through via our website. You can do that at spacenuts.io or spacenutspodcast.com. Just click on the send us your voice message on the right, or click on the AMA tab where you can send voice messages and written questions, which we love to get. Just don't forget to tell us who you are, where you're from, and while you're there, check out the Space Nuts shop and please leave your reviews for Space Nuts at your favourite podcasting platform. And thanks to those who have. We've had some amazing reviews in recent times, Fred, just fantastic. So I'm glad people are enjoying the show, and while you're enjoying it, we will keep doing it. And even when you're not enjoying it, we'll probably just do it anyway.
Just punish you by not giving you something that nobody enjoys.
Exactly.
It's called spite, isn't it? Isn't that why?
Yes. I've got a long documented list of grievances, spiteful incidents in my life. Yeah. Fred, we're done. Thank you so much.
A great pleasure, Andrew. I hope we'll do it again sometime soon.
It's a distinct possibility, as we just discussed.
Yes.
All right. Thanks, Fred. We'll see you.
See you later. Thanks, Andrew.
Fred Watson, astronomer at large, part of the Space Nuts team, and thanks to Hugh back in the studio who pushed a button and something happened that got us out live to our audience today. So thank you for watching live, those who did. Otherwise, you're listening to the recorded edition, which has been heavily edited, and so all the good stuff got taken out. But until next time, from me, Andrew Dunkley, thanks for listening to Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.